In the shadowed yards of 1950s, America, two-stroke diesels, beat out a rhythm that buried steam and drove a nation's freight for half a century. They fired every engine revolution, swapped power assemblies before lunch, and built an empire on speed and reliability. Yet, by the 2000s, they were fading, sidelined by new rules, rising costs, and rival technologies. What killed the two-stroke locomotive era? And how did the undisputed king of American rails lose the very game it once invented? The answer unravels with every turn of a piston. Every turn of the crankshaft, a two-stroke diesel delivers power. There's no pause, no wasted motion, just a relentless firing order that keeps the pistons driving, the generator humming, and the train moving mile after mile. This is the heart of the EMD 567, a uniflow scavenged engine where air rushes in through ports cut low in the cylinder liner, swept in by a roots blower spinning at the engine's side. Exhaust gases escape through 4 valves in the cylinder head, snapping open and shut in perfect sequence. The result is a steady, even-timed exhaust that defines the soundscape of American railroading. Inside the shop, a mechanic leans over an open block. The modular design of the two-stroke makes its magic clear. Each power assembly, cylinder, piston, liner, injector, and head, lifts out as a single unit. With the right tools and practiced hands, a crew can swap out a tired cylinder in under 90 minutes. Shop logs from the 1950s tell of teams pulling a pack before the morning coffee cooled and having the engine back on the line by noon. This speed wasn't a luxury, it was survival. Freight couldn't wait, and every hour a locomotive sat idle meant lost revenue down the line. The roots blower, a mechanical marvel in its own right, forces fresh air through the scavenge ports. Every time the piston reaches bottom dead center, this constant airflow clears out exhaust and fills the cylinder with a fresh charge, ready for the next power stroke. Unlike a 4-stroke, which fires every other revolution, the 2-stroke cycle is always working. Compression, combustion, exhaust, intake, each step blending into the next, with no break in the rhythm. That's how a smaller, lighter engine could make big power, crucial for hauling heavy loads across mountain grades, or pushing long freights through prairie winds. Every component is engineered for repeatability. The camshaft actuates unit injectors, delivering fuel with mechanical precision. Manuals, written in plain language for shop crews, spell out each adjustment, each torque spec, each troubleshooting step. Mechanics tuned by ear and by feel, learning the subtle differences between a healthy injector and one about to fail. The system rewarded experience, but it also forgave mistakes. If a cylinder failed, you didn't need to send the locomotive home. You rolled in a new power pack, checked the timing, and put the machine back to work. This was more than machinery. It was a way of thinking. Standard parts, predictable repairs, and a culture that measured success in uptime. If you're enjoying what you've seen so far, I hope you'll consider subscribing. It helps me preserve the history of these remarkable machines for future generations. Now, let's continue. The two-stroke's genius wasn't just in how it ran, but in how it could be kept running, day after day, by the hands and know-how of the people who worked the rails. Across the continent, the two-stroke diesel became the backbone of American railroading. F units, with their streamlined noses and thunderous exhaust, hauled freight from the Great Lakes to the Pacific. On the branch lines and the main lines, GP7s and GP9s, rugged, boxy, instantly recognizable, pulled everything from boxcars to grain hoppers, day and night. In the mountain districts, 6-axle SDs stretched out in long sets, their turbocharged 645 engines digging into the grades, dynamic brakes glowing red as they held back endless coal drags on the descent. The rhythm was everywhere. A steady drone at idle, a sharp bark under load, the high-pitched whine of the roots blower echoing off concrete walls in division terminals. Crews trusted these engines. They knew the quirks of each unit, the way a throttle notch felt, the subtle change in exhaust note when an injector needed attention. On winter mornings, after a night of snow and wind, a two-stroke would fire up with a cough and settle into its heartbeat, ready for another run. Dispatchers counted on availability. If a unit failed, the shop could swap a power assembly and have the locomotive back in service before the next shift. The manuals were clear, the parts interchangeable, and the system built for speed. Railroads like Union Pacific and Burlington Northern built their fleets around this logic, keeping hundreds of units in rotation, each one a familiar tool in the hands of machinists and engineers. Dynamic braking, a practical innovation of the era, let these diesels tame the toughest terrain. On the long grades of the Rockies and Appalachians, the resistance of the traction motors slowed heavy trains. The heat dissipated through rooftop grids, glowing in the chunk. For crews, this meant control, a sense of mastery over tonnage and track that steam could never quite provide. The two-stroke's reputation grew with every mile. Shop floors buzzed with stories of engines that ran through blizzards, across deserts, and over mountain passes with little more than routine care. Veteran engineers spoke of the forgiving nature of the design, how you could coax a tired unit home with a few adjustments and a practiced ear. For a generation, the two-stroke was more than machinery. It was a partner in the daily work of moving America's freight, a symbol of reliability and resolve. The confidence it inspired would define an era, even as new pressures began to gather on the horizon. In late 1973, the price of diesel fuel in America nearly doubled in a matter of months. For railroads, every gallon burned now cut deeper into profit. Procurement offices filled with fuel logs and cost projections. The numbers no longer favored tradition. They demanded answers. Burlington Northern's managers, facing invoices that rose week by week, ordered a series of fuel tests across their main lines. Dispatchers tracked ton miles per gallon, comparing the trusted EMDSD 40-2s, two-stroke workhorses, with newer four-stroke GEU 30Cs. The results surprised even veteran shop supervisors. Four strokes running the same loads, sometimes used 5 to 10% less fuel, especially on routes with frequent throttle changes or long idle periods. Every morning, fuel meters were checked before a train left the yard and again after the run. Paperwork piled up, columns of gallons, miles, and dollars. On the radio, dispatchers began instructing crews to adjust throttle settings, searching for every possible saving. The old logic of horsepower and reliability was now joined by a new metric, cost per mile. At headquarters, procurement analysts worked late, recalculating fleet expenses and projecting the impact across thousands of locomotives. Internal memos from 1974 called it a wake-up for legacy thinking. Shop crews noticed changes too. Locomotives were held back for efficiency checks, fuel contracts were renegotiated, and the pressure to justify every engine in service grew relentless. For the first time since the diesel swept away steam, the two-stroke supremacy faced a challenge not from mechanical failure, but from the price on the fuel dock. The search for more efficient prime movers was no longer theoretical. It was a daily, urgent reality, felt in every division and every ledger. New rules from the Environmental Protection Agency landed on railroad desks in the late 1990s, bringing a fresh kind of pressure. Locomotive builders now face strict limits on nitrogen oxides, particulates, and unburned hydrocarbons, pollutants that had once been little more than a footnote in shop manuals. For the classic two-stroke diesel, these requirements exposed a problem deep in its design. Inside a two-stroke cylinder, the piston drops and uncovers ports in the liner, letting a rush of air from the root's blower sweep through to clear out exhaust. But for a brief moment, both intake and exhaust paths are open. That overlap, essential for the engine's breathing, creates an escape route. Some of the fresh air fuel mix slips straight out the exhaust before it ever fires. This is hydrocarbon slip, unburned fuel vented directly to the atmosphere, a technical Achilles heel when measured against new clean air standards. Four-stroke engines with their distinct intake and exhaust strokes keep these paths separated. They can time combustion and scavenging precisely, burning fuel more completely and leaving fewer pollutants behind. Two-stroke builders tried to tighten injector timing, raise pressures, and fine-tune port shapes, but the overlap couldn't be eliminated without gutting the very principle that made these engines powerful and compact. As EPA Tier 0 and Tier 1 deadlines approached, 1998 for new builds, with retrofits soon after, engineers confronted hard limits. Retrofitting after-treatment systems like selective catalytic reduction or diesel particulate filters demanded space and cooling capacity that didn't exist inside car bodies designed for the 1960s. Extra hardware added weight, threatened axle limits, and forced tough choices between fuel capacity and emissions compliance. Shop studies logged higher under-hood temperatures and shorter service intervals, with some trials showing filter regeneration needed every 6 to 8 hours under load. The regulatory layer was now as real as steel or oil. The two-strokes breathing, once a symbol of American ingenuity, had become a liability in the eyes of the law. The challenge wasn't just technical. It was physical, economic, and, for many, personal. By the late 1980s, the railroad cab was no longer just a place for levers and gauges. Microprocessors began to take over. First in the GE-8 series, delivered in 1984, then spreading rapidly through the ranks. These digital brains didn't just monitor engine speed or temperature, they watched every wheel, every amp, every slip of traction. For the first time, a locomotive could sense when a wheel started to spin on wet rail and instantly adjust the power, keeping the train moving where older engines would have stalled or needed a lighter touch from the crew. Diagnostics became a new language for shop crews. Fault screens replaced scribbled notes and guesswork. A microprocessor could pinpoint a failing sensor or a misfiring cylinder, sometimes before the crew noticed anything wrong. This meant less downtime, fewer unscheduled repairs, and a new expectation. Problems should be found and fixed before they stopped a train. For railroads running longer, heavier trains across greater distances, this was a revolution in reliability. AC traction motors raised the bar even higher. Unlike older DC designs, AC motors could deliver massive torque at low speeds, making it possible to start heavier trains on steep grades and keep them moving through bad weather. But these systems demanded precise, stable power, something the new digital controls could deliver in real time, adjusting thousands of times per second. The whole locomotive became a network of sensors, processors, and feedback loops, each one tuned for maximum efficiency and grip. For two-stroke engines built around mechanical logic, this digital layer brought new challenges. Retrofitting sensors and control modules meant carving out space in car bodies never designed for them. Each addition brought more heat, more wiring, and more weight. Four-stroke engines, with their larger envelopes and more flexible layouts, handled these demands more naturally. The expectation shifted. A locomotive wasn't just an engine, but a rolling computer, expected to diagnose itself, manage its own power, and squeeze every bit of traction from the rails. In this new world, the old virtues of simplicity and hands-on service gave way to the promise of data and software, reshaping what it meant to be reliable on America's rails. Procurement offices turned into war rooms as the 1990s wore on. Gone were the days when a locomotive's fate rested on reputation or the comfort of familiarity. Now, every engine faced the same set of numbers. On one side of the ledger sat the trusted EMD two-strokes, SD40-2s, SD60s. On the other, four-stroke newcomers from GE, especially the -9 and AC4400. Every detail was measured, logged, and compared. Fuel consumption, shop hours, mean time between failures, and availability rates, all fed into capital spreadsheets that decided what would pull America's freight for the next decade. The numbers told a story that nostalgia could not rewrite. In mainline service, GEE's four-stroke AC units averaged just under 1 gallon per 1,000 gross ton miles, 0.97 to 1.05, depending on the route and load. The two-stroke SD40-2s and SD60s, long the gold standard, hovered between 1.2 and 1.3. For a single locomotive running heavy coal or intermodal, that gap meant burning 85,000 to 110,000 fewer gallons of diesel each year. Multiply that by a fleet of hundreds, and the fuel savings alone could tilt a procurement decision. Shop time became another decisive metric. Newer four-strokes needed 3 to 4 hours of labor per 1,000 miles, while the older EMDs demanded nearly double. Digital diagnostics and modular alternators let shop crews spot and fix problems before they sidelined a unit. pushing availability rates for GE's AC fleet to 95 to 97%. The two-strokes, even with their legendary serviceability, rarely topped 92. For a railroad, that difference translated to more trains on the road, fewer backup units idling in the yard, and a leaner roster overall. Break-even analysis sealed the case. Capital spreadsheets projected that a new four-stroke AC unit would pay for itself in 5 to 6 years, thanks to savings in fuel, parts, and downtime. The legacy two-strokes by then often needed 8 or 9 years to break even, a gap that grew as emissions, rules tightened, and shop costs climbed. Mean time between failures stretched to 22,000 or even 30,000 miles for the latest GEE units, compared to 15,000 to 18,000 for the best-maintained EMDs. Procurement officers, backed by CFOs and board presentations, followed the math. The numbers didn't care about the sound in the yard or the stories from the shop floor. They cared about cost per mile, asset utilization, and the certainty of compliance. In the end, it was the spreadsheet, not the whistle or the wrench, that picked the winners. In 1993, a single order sent a ripple through the industry. Burlington Northern's procurement office signed for a fleet of SD-70 Max, EMD's first AC traction locomotives. The contract was more than a purchase. It was a public bet on the future of American railroading. On the dispatch board, the change was immediate. Consists that once paired 3 or 4 SD-40-2s for a Powder River coal drag, now ran with 2 new AC units up front, their digital screens glowing in the cab. Crews tracked the numbers, fuel meters, amp readings, and trip logs. The SD-70 Max pulled heavier loads with fewer starts and stops, holding adhesion on wet rail where the old DC units would have slipped. Inside the procurement office, spreadsheets replaced stories. The boardroom table filled with life cycle cost models, warranty projections, and vendor support plans. A procurement officer, reviewing the final numbers, signed off with a remark that became legend in the shop. "We're not just buying locomotives, we're buying certainty." Across the yard, machinists compared notes. Some marveled at the new diagnostics. Others missed the familiar rattle of a two-stroke under load. One veteran summed it up between shifts. "These new engines tell you what's wrong before you even pick up a wrench. Used to be, you listened for it." The SD-70 Max rolled out alongside GE's AC 4400 CWs, each delivery tracked against fuel savings and shop hours. Dispatchers noted the difference on the main line. With AC traction, trains started smoother, tonnage moved with less drama, and breakdowns grew rare. Reliability, once measured in hands-on repairs, now came from predictive screens and vendor guarantees. At the end of each month, the numbers told the story. Lower fuel burn, higher availability, fewer idle units. The spreadsheet logic was no longer theory. It played out in every consist, every trip, every dollar saved. The decision was locked in, and the daily work of American railroading would never look the same. In 1994, BNSF placed its first major AC traction locomotive order, signaling a decisive shift away from two-stroke engines that had dominated since the 1940s. This film traced how the EMD 567 and its successors made American railroads efficient, with modular repairs and relentless power that set industry standards for decades. But as fuel costs surged after 1973, emissions regulations tightened, and microprocessor controls became the new norm. The advantages of the two-stroke design became limitations. Official procurement records and technical reports show that by the early 2000s, four-stroke engines offered lower fuel use, cleaner exhaust, and better integration with digital controls. Some design files and internal test results remain out of public reach, so not every detail of the transition is fully documented. Yet the evidence is clear. The two-stroke locomotive era ended not from failure, but from changing requirements. Today, preserved engines and short lines keep the memory alive, but the main line belongs to a new generation, proof that American railroading adapts as its challenges evolve. Thank you for watching. If you had the chance to work on one of these, or if you remember hearing that distinctive sound, I'd be genuinely interested to hear your story in the comments. And if you'd like to see more videos like this, please do subscribe. There's much more to come.